Good morning, everyone. I want to first start by asking if there are any questions on the, on the trigonometry we did last time. I know that was an awfully quick review, but at least I'm hoping that sounded really familiar to all of you. We're going to be needing that throughout this course a lot. So if that came crushing down on you a little bit too much, you probably want to see me. I can get you a book and some resources to help get you up to speed on that. But that's, anyway, can we talk more about the co-function identity? Sure. Where did you, okay, you must have gotten that from the website, Rachel. The co-function identity, I mean, we're not going to be using it too much, but here's how it works. Let me move the screen off to the right. The co-function identity simply says, first of all, a co-function, sine and cosine are co-functions. That is, all cosine is a sine with a co in front of it. And when you take the sine of an angle, that's the same as taking the cosine of the complement. Complement meaning two angles that add up to 90. Likewise, tangent equals the cotangent of 90 minus the angle, etc. That I think that's what you must be referring to as the co-function identity. Same thing with secant and cosecant. I don't use that real much in when I teach trigonometry because I teach people those behavior charts that I was speaking of yesterday in class. But it's certainly true. So anyway, that must be what you mean by the co-function identity. Any other trig questions? Or questions about the course, anything that can help clear things up on? All right. So just a reminder I've got on the screen, if you don't want to use the chat window or you don't want to speak up, please do. But if you don't, you can contact me with a text message, or if you have to, a phone call. It's not so wonderful to answer a phone call during a live video session, but that'll work. I mean, I'd rather have you do that than go silent. All right, so today's topic is inverse functions. Lesson 1.5 in the book. So let's dig in. Here are the learning objectives for this lesson. If they're kind of small, but find an inverse function informally and be able to verify that two functions are inverses of each other. Secondly, use graphs of functions to determine whether functions have inverse functions. Third, use the horizontal line test to determine if functions are one-to-one. And then find inverse functions algebraically. Those are the four things we're going to try to show today. All right. So I want to just show you that here I don't normally do this, but I borrowed from my website. That is, if we go to the accompanying calculus site, you will see that there's a lesson called inverse functions. And I have grabbed some of a couple of things from that site that I'm going to be showing you today. Okay, so back. So the inverse of a function literally undoes the action of a function. It reverses things. So if f of 2 equals 3, then f inverse of 3 equals 2. It just takes you from the answer back to the input. And yeah, and the notation for f inverse, you can see down here with the red arrow at the bottom, right down here. That red, down here. Now it's black. But you see that f with a little -1 exponent? That's telling you, that's saying f inverse of x. Okay, so how do you find an inverse? So if you look at the top, we have this function, f of x equals 2x plus 4. So the first thing you do is replace the f of x with a y. And then here's a wild one, you actually swap the x and the y. You put an x where the y is, put a y where the x is, and then solve the equation for the new y, which I did in this section right here. Okay, so I got y equals 1/2 x minus 1, 2. That is the inverse. And then it's stated at the bottom, f inverse of x equals 1/2 x minus 2. So I'll just repeat. To find the inverse of a function, replace f of x or g of x with y, and then swap the x and the y, solve for the new y, you now have the inverse. So here's another one. What was the one I just did before? That was 2x plus 4. I guess this is the same one, huh? Okay. So this is another way of looking, okay, this is the same problem, but I did it slightly differently. So you first replace the f of x with a y. Then you take the x and the y and swap them. And then you notice I subtracted 4 from both sides. I divided by 2. I mean, this is okay for an answer, but this is a little bit better. If you divide x by 2, divide -4 by 2, it becomes a -2. Okay. So now, here is how you determine if you really have an inverse or not. So let's check our answer. Let's see if 1/2 x minus 2, the one we just got, let's see if that's really an inverse. And the way you do it is you compose the function with its inverse. So, and you can do it either way. So at the top of the line here, if you take f of f inverse of x, so inside the f function, you want to plug in this value. So 2 times this whole thing, 1/2 x minus 2, plus 4. And when you work it out, you can see you first do the distributive property, and you get x. And that's, by the way, when you compose a function with its inverse, you should get x. It also works in reverse. If you do f inverse of f of x, this time you're using the 1/2 x minus 2 as your model, and you're plugging 2x plus 4 in. This 2, if you use the distributive property, you notice, oh yeah, you get x. So some of the assignment questions relate to, it says verify that this is an inverse of the other. This is how you would do it. You don't have to do it both ways, but you would compose the function with its inverse. I'm going to pause and just see if anybody has any questions there. Okay, let's do another example. So make that a little bit bigger. So this time our function is a little more complicated. It's x squared minus 3x plus 9/4, g of x. So the first thing we do is replace g of x with a y. All right, now swap the x. Well, first of all, I rewrote this x squared minus 3x plus 9/4. That's a perfect square trinomial. You guys, I don't know if you remember how to do that, but you should know that operation. That is the first term a perfect square? X squared is a perfect square. Is 9/4 a perfect square? Yep, it's 3/2 times 3/2. And if you take the square root of this, x times 3/2, that doubled is 3/2 doubled is 3. So this is a perfect square trinomial. So anyway, you can write it like this: x minus 3/2 squared. Now, swap the x and the y. So you just literally replace y with x, x with y. Okay, now solve for the new y. So the first thing I have to do is take square root of both sides. Right side, y minus 3/2. Left side, don't forget, you got to do both square roots, plus minus. And then just add 3/2 to both sides, and you have found the inverse. Okay. Anybody want to make a comment or a question there?
So if we didn't want to do like the into the square or the perfect square trinomial, but or we didn't know how, would we just put the y in for all of the x's?
That's correct.
Okay, thank you.
Yeah, that's a good comment. Yeah, but I mean, eventually I need everybody to spot that. But you're right. That would be the raw. That's exactly what you would do. Take x and replace all the x's, replace them with y, and all the y's, replace them with x. Yep. Okay, so now an interesting thing happens. We take some of those we just did, and if you take the original function, and that's plotted in, you can't see it, but it's a weak red. That's this line right here. This one on the outside. And if you put the identity function on there, y equals x, and here's the inverse in yellow. Do you notice that if you tilt your head along the line, the green line, you see how the inverse is the mirror image with respect to the identity. So the identity function kind of acts as a mirror. That will always happen with inverses. Okay, so there is, I guess you could say, a graphical check. So one more time, the yellow one, that's this 1/2 x minus 2. See, it's got a y-intercept right here of -2. And the slope is 1/2. So for every 1 up, 2 to the right. Okay. Or every 2 up, 4 to the right. Yeah. So, you know, you've got your you know, if I do go 1 up, 2 to the right, then we'd be right here. Okay, I want to just see. Did I get a message? No. All right. All right. So let's take a look at another. So here is a quadratic equation. This is the second one we did a few minutes ago. Let me get rid of this. Make this bigger. Okay, so this is the one we just did a few minutes ago, x squared minus 3x plus 9/4, and we came up with this for the inverse. So the original function, that's just a good old parabola, this red graph here on the left. And then I got the identity function in green again. And then you notice we have plus and minus square root of x plus 3/2. Well, the plus part is the yellow on the top, and the blue part is the bottom. That's the minus. And if you tilt your head to the side, you should see that we just have a parabola that's been tilted, and it really is a mirror image with respect to that green line. That will always happen with an inverse. All right, now we need to discuss something. in the book, they kind of get all hyper about this because the original red curve, the red parabola, that's a function. It passes the vertical line test, right? But when you look at the green and blue together on the for the inverse, they go, oh my gosh, that's not a function. And so they will get all upset that when we took the inverse, we didn't get a function. I'm more thrilled about the fact that, hey, the inverse really is a mirror image. So on some of the questions you're going to see, they're going to say, is the second an inverse function of the first? They will say this is not, because you see quite clearly it fails the vertical line test. And my questioning on my quizzes and tests will be more, hey, did you get an inverse? Yeah. Is the inverse a function? No. Okay. So anyway, they seem to be a little bit hyper about is it a function or not, but I'm more impressed with the fact that it's an inverse. Okay. So where are we? Yeah. So when you look at function notation, this is what happens when you do an inverse. Okay, f of 2 equals 3. F inverse of 3 equals 2. You see how the ordered pair 2 comma 3 literally got reversed, 3, 2. Or if you have g of 7 is 100, that's 7 comma 100. When you x is 7, the answer is 100. Well, when you do g inverse of 100 is 7. And so an inverse literally flips the ordered pair and goes back to the original. All right, I think we're going to move to, I wanted to talk about one-to-one functions. Okay, this is what we were talking. So what's a one-to-one function? Okay, this blue curve, f of x equals x squared, is a function. I know because I can see the vertical line test passes just fine there. Okay. But I know that when I find the inverse, it's going to be what? Rotated, and it's going to become that red curve up there. And you can see I followed the inverse, but it's not going to be a function. So we say that the blue curve is not one-to-one. What's one-to-one? That means that when you find the inverse, is it going to be a function? And this one is not one-to-one. And the way to test it is the horizontal line test. So for example, if we do a horizontal line test, you can see that it fails the horizontal line test. Therefore, when you rotate it 90 degrees, it's going to fail the vertical line test. So the blue f of x equals x squared is a function. Let me just say, is a function, but it is not one-to-one. So that means it's a function, but when you find its inverse, it won't be. That's in effect what a one-to-one function is. All right. So let's see what number 31 is. I'm going to look up, see what the problem is first here. Okay, so 31, if you can read, it's real fine print. It says in exercises 27 to 34, find the inverse of the function. So that's your first job. And then in part B, graph the function and its inverse on the same set of axes. C, describe the relationship between the graphs and state the domains and ranges of the two. Okay, so our function 31 is f of x equals the square root of x. All right, so let's go back. So the first thing I do is I interchange the x and the y. And then when I solve for y, I would square both sides and I get y equals x squared. Well, y equals x squared looks like this. Let me see if I have, let me change to black. So y equals x squared, sorry, very crude graph. Y equals x squared looks like this. And y equals the square root of x looks like this. Let me change colors. Y equals the square root of x looks like this, the principal square root. So why? Because there's no sign in front of that square root sign. That's called a principal square root. So, you know, you can see that it's not a perfect mirror image because, you know, if we take the, I'm sorry, it's too hard to sketch with my mouse. Let me try that with this. So if you put the identity function in there, you can see you only have half of a parabola. And so what's the domain of the original, or of the black curve? What's the domain? Left and right, because parabolas never get, they always get wider. What's the range? Only 0 and above. Now when you look at the red curve, what's the domain? The domain is x can only be positive. And what's the range? Y can only be positive. So anyway, you see, that's the kind of discussion you want to have. So let me write that for you a little bit. I should have written this as f inverse equals x squared. Okay, so for the function f, the domain because in the black curve over here, it goes forever left and right. The range is 0 and greater. And then when you, let me move this up a little bit. And then when you do the f inverse, that's the red curve over here. The domain is x is greater than or equal to 0. And the range is greater than or equal to 0. So you can, that's supposed to be a 0 there. So you can't, you see we don't have perfect symmetry there. You can't just reverse things. You really got to look at each problem correctly. So why don't, if we just go back here, why didn't I have a plus and minus in front of that square root? And that is simply because of the way the problem was stated. If we go back and look in the book, if we go back and look in the book, you see how it just says 31, f of x equals the principal square root of x. So because of that, what we have is just the red, you know, the red curve, and it's not mirrored with the negative on the bottom. So you got to be a little bit careful with those. Let's take a look at number 65. And the directions for 65, let's take a look at what those are. Okay, sorry, I can't make this any bigger. But for 65, it says, find f inverse of a for the function and the real number a. So for 65, we've got this x cubed plus 2x minus 1, and a is negative, I'm sorry, a is positive 2. So, all right. So first of all, what's f inverse of a? Now, if you try finding an inverse, you're going to find yourself in trouble here. Let me show you what I mean. If you, this part right here, is where I tried to find the inverse. Okay, so I swapped the x and the y. I first of all replaced f of x with y, and I swapped them. Well, when you can't really solve this for y. I mean, when you get down to here, what are you going to do? Divide both sides by y squared plus 2, but then you're going to have y on both sides, so you're kind of stuck finding an inverse here. So let's abandon that, and let's go back and let's think of it this way. What's f inverse of a? So in other words, when the answer is 2, what value of x would have had to cause this thing to come out to be a 2 in the original function? Well, if 2 equals x cubed plus 2x minus 1, just by looking at it, can you see that it works if x is 1? Because if 1 cubed is 1, 2 times 1 is 2, so 1 plus 2 is 3, 3 minus 1 is 2. Oh, yeah. So that one you can't really solve by algebra, but you can with a little bit of logic. So you got to watch out for that. Let's see. Yeah, I just wanted to show you this one. It's just another example of a parabola where when you find the inverse, you get, so the original function's up here at the top. And here's where I got the inverse. And when you plot the two, you see how you get beautiful mirror imaging with respect to the green identity function. Again, is the inverse a function? No. Each half of it is, but not the whole thing. Why? Because it fails the vertical line test. Okay, now we need to talk a little bit about trig inverses, trigonometry inverses. So here's the 101 through 106 section. So, all right, number one, well, first of all, it says at the top, use the figure to write the expression in algebraic form given y equals the arc cosine of x. Okay, so, and y is between 0 and pi over 2. So here's angle y. The cosine of y so y equals the arc. So the cosine of x, the cosine of y is x. So what's cosine? Leg adjacent divided by hypotenuse. And x over 1 is x. So that fits this statement. Y, that means x is the cosine of angle y. Okay, so now that we know that, we can use the Pythagorean theorem to find that remaining side there. So we've got one leg squared plus the other leg squared. I don't know, let's call it k. Just for a moment, we'll call this k. Equals 1 squared. X squared plus k squared equals 1. And then we want to find out what k is. So k squared equals 1 minus x squared, and k equals the square root of 1 minus x squared. Okay, now that we know that, now can you tell me what the sine of angle y is? So now that we know all three sides of the triangle, what's the sine? Opposite over hypotenuse. So yeah, and that would be over 1, so I don't have to write it. What's the tangent of angle? Let's do the cotangent. What's the cotangent of angle y? Well, tangent is opposite over adjacent, so cotangent is adjacent over opposite. So do you see how you can solve all of those? You first have to find that remaining side of the triangle And then the rest of these should all fall. Okay. See what the assignment is. So 1-6. Here we go. Well, anyway, the 1-6 assignment is right there. It's not real clear, but you should be able to see it. It hasn't come back in yet. My apologies. Let me try reloading. See if that does it for you. But it's of course on your website. There we go. So the 1-6 assignment, you can see it there. There's 5 different sections of odds that they're requiring. I'm in the wrong place. You're right, Richard. It's 1-5. Okay, so let's get rid of that. Yeah, I got it. You're right. We're on 1-5, so it's a 1-5 assignment. So anyway, if I can figure out, here we go. So there it is. Now you notice that 9 to 12, it doesn't say odd. That means you really should do all of them. 87 to 94, it doesn't say odd, so you should really do them all. And then here we're back to odds again. So there's the assignment. Now, questions? If I went too fast, I'm happy to go back and go over something if you would like. Well then, I wish you a good morning. I hope it looks like we're going to have sunshine today, and it's going to at least get close to freezing, close to 32. So I hope you have a good day. Thank you for joining me. I will see you tomorrow.